Hello, everyone. This is Mix K. Today, I am just going to talk a little bit about topic 6.5 energy and phase changes. So, I'm not going to be in today if this is the original time you're watching this video. So, please make sure you are recording some notes down. I will be coming around to check for notes to make sure you did watch some of these. So when we look at these, actually, maybe I'll just put them in a puzzle. Don't worry about that. So when we look at these diagrams, they represent energy and temperature. So it is heat energy absorbed. Usually this is in joules or kilojoules, and temperature change. Okay. Now, for this one, as we notice, the temperature is going up. So this would be a heating curve. If we inverted it and it was going down, it would be a cooling curve. Now, when we look at this, we're heating up a substance. And so we are looking at it doing a phase change from solid to liquid to gas. If it was reversed, it would be gas to liquid to solid. Now, you'll notice that we have these regions of increase and these regions of plateau. Region of increase, region of plateau, region of increase. Where as heat is being added, because if we look, heat is being added throughout. We are moving down the x-axis. So we are adding heat energy throughout this process here. If it was a cooling curve, we'd be removing heat throughout the process. And there are times where the temperature increases. But there's also times where the temperature stays the same. Temperature increases, temperature stays the same. Now, these regions where we are on an increase, okay, on these increases, the heat energy is going towards increasing the kinetic energy on average, which is increasing our temperature. So in this first region, our solid particles are gaining energy and their kinetic energy is increasing, so their temperature is going up. But you'll notice at a certain point, and this temperature here, notice this is water. Okay, so this is water. This temperature here at 0 degrees Celsius, the temperature stops increasing because this is where we have hit our melting point. We abbreviate it sometimes MP, melting point. Now, melting point is the temperature at which it melts. Okay. Now, we can also call this the freezing point if we were going in reverse because they happen at the same temperature. Now, sometimes these are called slightly different things. You might see for solidifying something, for freezing something, it might be also written as fusion because those substances are coming together. Now, if we talk about the temperature at which this happens, that is the melting point, the freezing point, okay? But if we talk about the amount of energy, that is a little different. The amount of energy to get it to melt is called the heat of fusion. Now, you'll notice I say fusion here because the delta H of fusion is the same as the delta H of melting. But we don't even have really a clever name for it because we just use fusion. Now, there's something wrong here. One of these should have a negative sign. Because in one case, we are breaking attractions, which takes energy, it takes to break. And the other one, we're forming attractions, which releases energy. So in fusion, our solid is forming, so that releases energy. So this one should be negative. Okay? But they mean the same thing. So if it's a negative value, it is releasing energy, so it is fusion. If it's a positive value, it's taking in energy, so it's melting. Now, what would this delta H be? It would be this span on our graph because that is how much heat was absorbed over the course of this time. Or not time, but over the course of it fully melting. Now, once it fully melts, now it can go back to doing this process, but this time it's happening to the liquid, where the liquid is now increasing in energy and so increasing in temperature. But why did it plateau? Well, all of that energy stops going into the kinetic energy and goes into breaking IMFs / bonds, depending on the substance. Okay, attractions. So during this melting process, no energy is going into the kinetic energy, and all of it is going into breaking these IMFs. So our temperature doesn't increase, but our particles separate. The same thing can happen at the boiling region on the graph, okay, where you'll notice it's much bigger because we're breaking more IMFs. Okay, but we could find the delta H of vaporization for this one. Same thing about the delta H's. So vaporization, they are separating. It takes 2 breaks. So that would be negative. And that would be the same as the condensation one, but we don't even have a good word for the condensation one because we just call it vaporization because they are the same values. Okay. Now, again, once it fully evaporates, that energy can go back into increasing the kinetic energy as opposed to breaking IMFs. Now, what can we do with this data? Well, we can actually calculate how much energy would be needed to do any one of these processes. So when we would be going from in this liquid phase here, we would be using the specific heat of water like we did in class the other day. We have a different specific heat for water as a gas and water as a solid. So we would need to use those specific heats. So on the angles, we use specific heat to determine how much energy has changed. And that you just use your Q equals MC delta T equation. But if we are on a plateau, we need to use the delta H value to figure out how much energy is needed or absorbed. So when you have a phase change, you might have multiple steps because if you are going, I'm going to erase some of this. If you are going all the way from solid to liquid to gas, there are different values you would need to use. So when you go from your solid to your melting point, you would need to use your specific heat of solid water. From your melting point to when you're fully a liquid, you would need to use your delta H of fusion. When you're going from your fully melted to boiling point, you would need your specific heat of liquid water. From here to here, you would need, for boiling, your delta H of vaporization. I forgot the H. And then once it's fully evaporated, you would need your specific heat of water again. So you might be asked, how much energy would it take to increase a sample of water from liquid at 100 degrees to gaseous at 140 degrees? And so then you would need to figure out how much energy did it take to boil it, and then how much energy did it take to increase the temperature. So you might have to do a Q equals, no, that's over here. Q equals MC delta T to find this Q, and then do a delta H value with our stoichiometry from our last video to figure out this value, and then add them all together. Now, let me show you an example of how that might happen, and I'm going to actually go through this WeDo problem with you guys. So if we look at this phase diagram for, not the WeDo, the I do problem, I'm just going to explain it. Okay, if we look at this diagram, they're giving us the values. So it takes 2.3 kilojoules per mole of energy to melt our mercury, and it would take 58.6 kilojoules per mole to melt a mole, to evaporate a mole of mercury. Okay. And so if we were given our value for how much mercury we have, it's now just simply a stoichiometry problem. So here it says to freeze. So if we're looking at our graph, here we have our solid, our liquid, our gas. So to freeze it would be heat of fusion. We're fusing it together into a solid. Okay. Now they say 100 grams of Hg at its melting point. What that little clue is there is that it's at its melting point already, so we don't need to worry about the fact that it's a liquid cooling down or it is a gas in some other state. So they're giving you the little hint that this is just a one-step problem, that you are starting at the melting point, so you only need to worry. Oh no, I'm making a mess up my point. Where's my eraser? Okay. So you're already at the melting point and they want to know how much energy is it going to take to freeze it. So they're only looking for the energy change from this point. So we can use the delta H value of fusion here. And now it's simply a Stoich problem, kilojoules per mole. So we can turn grams to moles. So grams and grams cancel out. And now we are using this value as a conversion. Now notice it's negative. Why did they use negative here? Well, we are doing heat of fusion. It is freezing. We are forming attractions, which means we are releasing energy. So it should be a negative sign. This is an exothermic process. Okay. And then it's just a matter of plug and chug. Now, what if they also asked you something like, what is the amount of energy it would take to, they don't really give me that in that graph. Let me see if there's another one I can use. Pause. Can I pause? No, I'm not pausing. But they could say, okay, instead of it being at its melting point, maybe it's above the melting point. Maybe it's at a higher temperature. Like, I don't know, let's say it's at 600. Well, now I need the specific heat of liquid mercury to solve this problem. Because now I have an extra step. I need to figure out, let me erase some things, how much energy it takes not only to get from here to here, but if I change this to not being at its melting point, but being at, I don't know, 600 degrees Kelvin, I now have to figure out how much energy it takes to get from here to here. So we already figured out in this problem that this amount of energy is negative 1.1, I'm not writing all of that, kilojoules. But I don't know how much energy it would take to cool that mercury down enough to reach its melting point and then freeze it. So now I have to do a separate problem. And now I'm doing a Q equals MC delta T problem. Now, I don't know the specific heat of liquid mercury, so let's go look it up. Specific heat of liquid mercury. Let's see if it comes up for me. Okay, that's in joules per kilogram. I don't like that. Kilojoules per mole. Point. You guys watching me struggle right now to try and find kilojoules per mole for liquid mercury? Pause. Okay, I realized I was being silly and looking up the wrong units. So now I have it. So 0.14. We're just going to go with that one because it doesn't really matter. We're over here. So now I need to go in and solve for the Q of actually cooling that liquid down. So this Q value is how much energy is released when I cool it down, when I start bringing them closer together. Okay. So my mass of my sample was 100 grams. That's still the same. My C value was 0.14 joules per mole or gram C. Notice, really important in these problems, this one's in kilojoules. This one's in joules. They're not very nice to us. So that means we need to be careful when we go to add these two values together and make sure they're both actually in the same unit. Now for my change in temperature, excuse me, I would like to draw again. I had 600 to the melting point, which is 234. So 600 Kelvin. Oh, guess what Mix K did? Very silly mistake. I did the big number first. We want to do final minus initial, not initial minus final. So I have to go back. I need to do 234K minus 600K. So now it's just a matter of solving out for this Q value. So Q here times 0.14 times whatever this difference is. Hey, fun fact, if it's easier for you to do big minus small, that's totally fine. I do it all the time, but you have to make sure you flip the sign to negative after. This is negative 366 Kelvin times 0.14 joules per gram C. Remember, the C and the K don't matter because it's both change in temperature. So change in temperature is the same for Kelvin and Celsius. And now I just got to plug this into my calculator, which I don't have. So I'm going to go do that and pause and figure out what it is. All right, so I got this, but this is in joules. So I need to divide this by 1,000 before I add them together. And this is negative. Okay, so it would come out to this. Okay, negative. Now I can add my two values together. Sorry, I'm taking up the we do space here. Okay, so I have the energy it took to cool down the liquid to the melting point was this. And the amount of energy it took to, that should be in kilojoules now. That should be in kilojoules now. Okay. And the amount of energy it took to actually freeze that sample. And now I just need to add them together to get the amount of energy it took to take a sample of mercury from 600 degrees, not degrees, Kelvin, down to the melting point and then freeze it. Okay. I'm not going to bother adding these together right now. I'll do it. 6-6.26, kilojoules. Okay. So sometimes you will get these as a two-step problem, but all you have to do is have the data you need. So when it's heating or cooling, it is the specific heat. When it is melting or evaporating or doing a change in state, it is the heat of fusion or the heat of vaporization. Okay, I hope that was helpful. Have a wonderful day, and I will be posting this shortly.